All right, so let's take a look at section 6.3. We're going to split it into 3 days. We're going to focus just on sine and cosine graphs for Monday, Tuesday, Wednesday. When we do 6.4 on Thursday, we're going to look at all the other ones. So we're going to kind of do a lot with sine and cosine, like a lot of depth. But then the other ones, like tangent, cotangent, secant, and cosecant, not as much graphing with those, not as much depth. All right, so we've studied lots of kinds of functions this year. We've studied, like, very early on, we did quadratics. We've studied radical functions, rational functions, exponential functions, log functions, lots of kinds of functions. Well, we haven't studied any functions that are periodic up until now. So I'm going to draw these on the calculator first so you can kind of see what a periodic function looks like. And then I think you'll be able to tell me a little more about it if I show you a picture. So let's start with sine. And I'll graph cosine at the same time. So sine is in blue, and cosine is going to be in red. So there's a graph of sine and cosine at the same time. Right? So just kind of put that off to the side. Right? That's what it looks like. Let's move it up a little bit. All right. Now, before you think you know what a periodic function is, let me show you another one. This is tangent. Tangent looks a lot different, but it's still what we call a periodic function. So looking at the examples on the board, anyone think they have an idea of what a periodic function is? Yeah?
It's a pattern that is constantly repeating a certain motion.
Yeah. Basically what happens is values keep repeating. Right? When you get to a certain point in the graph, it's like I've been here before. I've already seen this point before now. So what happens is the y values keep repeating. With sine and cosine, they're always between -1 and 1. With tangent, that's totally different. We'll look at that later on Thursday. Okay. So what happens is if you look at the sine and cosine, it might start at 0, goes up to 1, back to 0, -1, and back to 0. Those numbers that I just said, 0, 1, 0, -1, 0. That's the pattern for the y's. Okay. And those numbers describe the important points. Obviously, there's other y values in there too. But 0, 1, 0, -1, 0 describes the intercepts, the high point, and the low point. So those values keep repeating in exactly the same sequence over a given set of x values. Okay, so I'm going to explain what I mean by that last part, over a given set of x values. All right, so if I take, let's take the graph, let's put sine back. You know what? Let me make it. If you go to Zoom 7, that's kind of a good one for when you graph trig stuff. Zoom 6, we use that a lot, but Zoom 7 is better for trig, and it's called trig. All right, so let's look at that. So the y values repeat over a given set of x values. So if you start, let's put this here. If you start here, and end there. When you look between the green lines, that section represents what's going to keep happening over and over. I could copy and paste what's inside the green lines, left and right, forever, and I would get the picture of my graph. This, from here to here, that's the set of x values that I need to go through before I repeat. So if you look at it, you might think, oh, you got to go 1, 2, 3, 4. Yes, you do have to go 4 marks, the way I set it up, but each mark isn't 1 unit. We'll talk about what each mark is. Okay, so on this graph, what you're kind of looking at here is the x-axis represents an angle. Okay. The y-axis represents the sine of your angle. All right, so like if you said to me, all right, 90 degrees. 90 degrees is actually right there. That's what that first mark is. Each mark is 90. So if I go to that first mark, say 90 degrees, it's right there. And if you said, well, what's the sine of 90 degrees? I would say 1. It's right there. If you said, what about the sine of 180? I'd say, okay, that's 2 marks. And that one's right there. Sine of 180 would be 0. What if you went to 270? Right, I'm just picking ones that are easy to do. I can do anything, but those are easy ones. 270, that's the third mark, if each mark is 90. Bless you. So the sine of 270 is -1. Okay, so what I'm just trying to show you is the x-axis is an angle. The y-axis is the sine of that angle. Okay? And you probably can guess now how far you have to go through all the values before they repeat. It's 4 marks, but how much did I say each mark was? Yeah? 90, so 90 times 4 is 360. If you go through 360 degrees, you go through a full, and there's actually a special name for that, I'll tell you in a second. But you go through a full section. Right? And we're going to do a lot of this in radians. So instead of each mark being 90 degrees, it's going to be pi over 2, because pi over 2 is the same as 90 degrees. All right. So the length of that interval that I just showed you left to right, I told you it was 360 degrees. But does anyone remember from last week? 360 degrees is what in radians? It has pi in it, but it's just not pi. It's something in front of pi. It's 2 pi. So that's what I'm telling you right here. The length of that interval from left to right that you have to go through, and I said I'd give you the name of it. There's the name right there. It's called the period of the graph. The period is the length of one section you have to go through, after which you're going to repeat what you've already done. So for sine and cosine, the normal period is 360 degrees, or as JD just said, 2 pi radians. Now, that's what we call the normal period. You can change that. Okay. If I were to graph something like this, let's graph sine 2x. Watch what I've just done. It still goes up and down the same amount. But what I've done is by putting a 2 in it, I've made it repeat faster. So now it doesn't have to go as far as 2 pi to go through one full period. It's doing it faster on the red one. And that's what we're going to talk more about tomorrow. So you can change this number. But if you just leave it alone, the normal period is 2 pi. Another name for a period is also called a cycle. One full cycle of the graph. Okay, so you'll hear me use both words kind of interchangeably. Is anybody in electrical? Yep. So this term is used in electrical, cycle, especially when you're talking about alternating current, right? So like the kind of current we have in the wall outlets in here, not the kind of current in your car. That's different. But in the wall outlet, it's alternating current, and it runs at 120 volts. Or ideally, that's what it should run at. And there's one other thing that it has to run at. And if this number isn't correct, then we have a problem. And it's different in like European countries than us. And yes, Europe has different voltage too, but I'm talking about something different. Yep.
Frequency?
The frequency of the electricity. And the frequency is measured in hertz. And in a US outlet, the frequency of alternating current is supposed to be 60. That's what the current is supposed to run at. And hertz stands for cycles per second. So that's where you see the term cycle used. They don't call it periods per second in electric. They call it cycles per second. I think in European countries that number is 50.
That is correct.
And you might think, big difference, 60, 50. If you plug something in that only works on 60 hertz into a 50 hertz outlet, something like with electronics, like a computer or like something really like sophisticated, it'll ruin it. But most things now can run on both. Like if you look at like a lot of chargers, they get that big bulky thing that you plug in. If you read it, there's like a lot of little stuff on it. A lot of them say 50/60 hertz, meaning you can plug it in a US outlet or you can plug it in a European outlet. It'll work in both. So that used to be a problem, like more when people would travel to other countries. They didn't have devices that would work on both, like a hairdryer or something. Now, if you've got a hairdryer, there's probably a little thing you can like turn on it, change the voltage to European versus US. But that's just an example where they use cycles. Okay. All right, so when you want to graph sine and cosine, you really need about 5 points. Okay? Like if you're doing a line, you only need 2. If you wanted to draw like a parabola, you might need 3, to get the shape of it. But with sine and cosine, you really need 5. And the 5 points that we pick are right here. These 5 points represent all the x-intercepts. In this particular section of the wave, there's 3. The highest point and the lowest point. That's what we always do. We always want to sketch all the intercepts, the highest point and the lowest point. Are there more points you could sketch? Sure. I mean, you could find this one, you could find that one. I mean, the more points you get, the better it's going to look. But I think 5 is enough. Okay. Also, if you go back and look at the picture of the wave, I'm just going to go back for a second. Does it look like that wave ever stops? No, it doesn't. It goes on forever. Well, when we sketch, we've got to decide how much are we going to sketch. This is what your sketches are going to look like. You're going to sketch one cycle of the wave. Why just one? Well, I assume if you can sketch one, all you'd have to do is copy and paste that, and then you could sketch another one. So really, you only need one cycle. Now, how far apart did I say each one of those was in degrees? 90. So there's the labeling except in radians. That's 90, 180, 270, 360. So they're all 90 apart. In radians, that's pi over 2. And if you wrote them all with a denominator of 2, you would see a pattern. The first one is 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. The next one would be 5 pi over 2, 6 pi over 2, 7 pi over 2, 8 pi over 2. It just keeps going up by pi over 2. The reason it's a little harder to see the pattern is because we don't write it as 4 pi over 2. That can be reduced. We don't write it as 2 pi over 2. That can be reduced. But that's the pattern. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. Okay. Any questions on that? And that is an accurate sketch of the sine function. Okay? But that is to scale and everything. It's perfectly accurate. So anytime that we graph a transformation, okay, and the 4 transformations we're going to study are the same ones we've done all year. You can shift left and right. That's 1. You can shift up and down. That's 2. You can stretch left and right. That's 3. And you can stretch up and down. That's 4. The nice thing is when we do transformations, every single transformation is exactly the same as what we've studied all year. So if you know what a vertical stretch looks like for a parabola, then you already know what a vertical stretch is going to be for a sine function, like where the number would be in the problem. All the transformations are the same. But we can't do any transformations unless we know where sine and cosine start. Okay, it's kind of like if I gave you directions and I just said, oh, just head 2 miles that way. And that was the exact direction somebody wrote on a piece of paper. Head 2 miles that way. Well, unless they tell you the starting point, like from downtown, head in the city, like from downtown in Leominster, head 2 miles, east, put a direction. They got to tell you where to start from. Okay? So that's what these tables tell you. The first table are those 5 green dots. 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, 2 pi, 0. It's those 5 dots. And those are the 5 coordinates for the first cycle of sine. Well, first positive cycle, because it goes on forever. So how do you say which cycle is the first one? Well, first positive cycle. So every transformation we do, we're going to use that table. Cosine is a little different. If I go back and put the picture back up for sine and cosine when I graphed them at the same time, they look, let's just make it bigger. I mean, they look kind of the same. They're both waves. But it's almost like one of them is it's a shift. Like if you took the red one and shifted it to the right a little bit, it would be on top of the blue one. Or if you took the blue one and shifted it left, either way. So we're going to see the same kind of values. Same highest point, same lowest point. But they start at a different spot. The blue one started at 0 on the y-axis. The red one starts at 1. 1, 0, negative 1, 0, and then back to 1. So that, what I just said, that's the order. 1, 0, negative 1, 0, 1. Same x values. Okay, we're going to stick with those x values because those are nicely spaced. Right? They're all 90 degrees apart. And that's important. Every time we make a table, your 5 points in the table are all going to be nicely spaced. They're not just going to be random numbers. Okay, so our goal when we graph is to figure out what happened to the points in this table. Like if we shifted them up, we'd have to make an adjustment to the y values. Or if we shifted it left or right, we'd make an adjustment to the x values. For today and tomorrow, we're only going to do one thing at a time. Meaning, if we take in this function and we shift it up, that's all we're going to do. We're not going to shift it up and left at the same time. Okay, we're going to do that on Wednesday. But for today and tomorrow, one transformation per problem. Okay, any questions on the original tables? So I'm going to come back to these for every problem we do today. All right, so this is what's going to happen. This is true for today and tomorrow. Because we're only going to do one transformation per problem, one column will stay the same, either the x's or the y's, and the other column will change, either the x's or the y's. Okay, so this is only for Monday and Tuesday. If you start getting into transformations that say shift it up and left at the same time, then both columns change in those original tables. So since one column is going to stay the same today, depending on the transformations we do, either the x's or the y's, all you're going to have to do for half the table today is copy down the table I already gave you. For half of it. The other half is going to change, but half of it won't. All right. So everything I just explained about like periodic functions, those original tables, that's all background information for every transformation we do this week. For the rest of today, I'm going to talk about two specific transformations. The first one is called a phase shift. Okay, we're going to do both of the shifts today, and we'll do both of the stretches tomorrow. So, phase is just a fancy word for horizontal. When they talk about trig functions, every transformation except vertical shift has a special name. You can call it a horizontal shift, but when you deal with trig, they call it a phase shift. That's what they call it. So it's just when the graph is moved left or right. You could say shifted or translated left or right. Now, just like all the functions we've studied all year, if I did something like this, that's a parabola shifted 2 units to the left. Remember, it's always the opposite. So plus 2 would move it left. This is a square root function shifted 2 units to the left. Well, sine and cosine are exactly the same. If you add or subtract, changes left or right. But if you add or subtract inside the parentheses, that's a horizontal shift. We just have to remember which type of number shifts it with which way. Minus moves it one way, plus moves it the other. And when it's inside the parentheses, it's always the opposite of what you would think. All right, so when I picture a number line, I think the negative numbers go to the left. But when you're doing a phase shift, x minus a number shifts it right. And that's the way it's worked all year. It's always the opposite. So if x minus a number is going to move it right, what about x plus a number? That's going to move it, yep, it's going to move it left. So really, now we have an accurate term to describe the difference between sine and cosine. They are phase shifts of each other. And I'll show you that right now. Okay, let's skip that one. All right, so let me graph sine and cosine again. Okay, so there's sine, and there's cosine. They're exactly 90 degrees off. That's the amount of phase shift. So I'm in radians, so 90 is pi over 2. I'm going to take the graph in red, and I'm going to move it to the right, just enough so that it's exactly the same as the blue one. What do I do if I want to move something to the right? Is that plus a number or minus a number? Minus. And I said that they were 90 degrees off, which is pi over 2. So take the graph in red and minus pi over 2. Okay. What I'm doing is a phase shift. I'm shifting the graph in red 90 degrees to the right. Now watch what happens when I graph them. That's the same. That's sine. But there's cosine. It's exactly the same. So sine and cosine are phase shifts of each other. All right, so we've got those two original tables. How do we adjust those tables now once you do a phase shift? Well, let's think about what's changing. You have x values and you have y values. If you move something left and right, which values would that affect? If you move left and right, does that affect the x values of a coordinate or the y values?
X.
It affects the x's. So what that means is the y's are not changing. The y's stay the same. So when we're creating our new table of 5 points, you're going to go to the original table that I gave you in your notes, and you're going to copy the y values down. They stay exactly the same. Now, which table do you use? Well, it depends on if it's a sine or a cosine problem. If it's a sine problem, use the sine table. Cosine problem, cosine table. So the x's are the ones that are going to change. So how do we find the new x's? Well, let me put up a problem at the same time and we can kind of look at it. What you're going to do is determine what has been added, or in this case, subtracted. Okay. So look at the argument. The argument is the thing in parentheses. I have subtracted a pi over 2. So now I think in my head, okay, minus pi over 2. Minus is going to move it which way? It's going to move it to the right. So if I want values to move to the right, if I think of my x-axis, to move things to the right, I have to make the numbers bigger, right? If you make the numbers bigger, that moves everything to the right. So I would actually have to add something to all my x values to make them bigger. What would I add? I would add that number right there. So what you end up doing is you always do the opposite with a phase shift. Okay. We're going to study 4 transformations. 2 of them you do the opposite. 2 of them you don't. Phase shift is one that you do. You do the opposite. So somehow you just have to remember that. Okay, so you look at what's been added or subtracted, and you do the opposite of that to every x value. So here, plus pi over 2. When I go through this one, I'm going to minus pi from all the x's. When I do this one, I'm going to minus pi over 4 from all the x's. Okay. Any questions on the 2 steps before we do some examples? Now, technically, you can shift by any amount you want. The common shifts that we do are usually a 90-degree shift, a 180-degree shift, and a 45-degree shift. Could you do a 33.4-degree shift? Sure. But it's just it comes out kind of messy. So we stick to the shifts that come out a little nicer. All right. And you know what? Before we do that, let me play something. All right, so this program lets me generate different kinds of sounds. Like I can change the volume, I can change the pitch, I can change all kinds of things. What I'm going to change is the phase. To do this accurately, I need 2 speakers, which I do have. There's a left and a right speaker in that soundbar. And I'm not going to change the volume. Okay, volume is going to stay exactly the same. If I was changing the volume, you'd see me dragging the volume thing up and down. So that's going to stay the same. All I'm going to do is I'm going to take this and I'm going to start moving the waves out of phase till they get to a point where they're completely out of phase and then back in phase again. If you do a 360-degree phase shift, it's like you haven't shifted at all. It's lined back up. So I'm going to drag that and I'll let you kind of listen to it and you can tell me what you hear as I do it. Any thoughts what you're going to hear as I just start sliding it? So you think the pitch is going to change? All right, so that's one thing that could change. Any other thoughts? Michael? You won't be able to hear it? Well, technically you would be true. What complicates it in here is the sound, because this is enclosed. So the sound is going to echo off every wall. So because of that, you'll never completely not hear it, but that's kind of what's going to happen. As I slide it, some people might hear it get quiet, and some people might hear it get louder. All right, so let's see what happens. So as I slid it, what did you kind of hear? You heard nothing at all. So where Jake was sitting, it didn't change at all. Same volume, same pitch. He heard no change the whole time, just a constant sound. Yeah?
I heard the same sound, but it felt like it was coming from different parts of the room.
So it sounded like it was moving?
Correct.
Yeah? Yeah?
I heard like it was up and then it was down a little bit and then it went back up a little bit higher towards the end.
So it got like louder and softer?
Yeah.
A little bit? I didn't change the volume.
Yeah, it was louder at the beginning and then like softer in the middle and then towards the end it got louder.
It got louder. So depending on where you're sitting, you will hear
Well, me and Jake are right next to
different
each other.
things. Yeah, I mean, even just being like 3 feet apart, I mean, it could be your hearing too, I don't know. But Jake will move to a different spot. So depending on where you're sitting, you will hear different things. And that's why when they design like music halls, they try to make it so that it sounds good everywhere. If it got quieter for you in a certain spot, that means that particular phase and that frequency, that's kind of like a dead spot in the room. If that was being played like at a concert or by an orchestra, it wouldn't sound good in that spot. That sound would be quieter than it should be. And that's because of the way the phase of the sound is interacting and the way it's echoing in this room. So I'll play it again and we'll see if, let me put it back. You know what, I can just leave it there and we'll go the other way. Got very loud for me right there. And now it's getting very quiet. That's the quietest for me. But that's because I'm standing here. I heard other people say, well, no, it got loud when I thought it got quiet. And it's just because of where I'm standing. So depending on where you sit, you'll hear different things. Yeah?
At the first time, like before you stop, I heard it like crackle a little.
Crackle?
Yeah.
That might just
Like
be the
stop a
speakers.
little.
It could be your hearing. I'm not sure.
It could be those, yeah.
Yeah.
Yeah, it shouldn't crackle. It should stay pretty. It might. I mean, I hear a little distortion in the speaker. It's not perfect because it's not like a $20,000 sound system. So that could be part of it too. Yeah. Somebody else had a thought? Or? Yeah.
The first time we went through, at one point it got to like I couldn't hear it, but when you were going the other way, I could hear it the entire time.
You could hear it, yeah.
And it didn't get as quiet.
So the best way to do this would be if you could do it in a place where it couldn't echo. Because even though you don't really hear an echo, there is an echo in here. Like my voice hits, it hits your ear first. It bounces off that wall. Some of you hear that. The rest of it bounces off the front wall, and then it bounces back to you again, and some of it hits the. So the sound is just bouncing all over in here. That's kind of a problem when I do my recording. So I have a special thing that tries to take out the echo. Otherwise, it sounds like there's a lot of echo. You can hear it better when there's no desks in here, no posters on the wall, and you're like the only one in here. Then it really echoes a lot. But if you could do this outside, where there were no walls, set up 2 speakers, stand at a certain spot, and have somebody change the phase, there should be a point where you almost can't hear anything. Like it gets almost completely quiet because there's no way for the sound to echo if you're standing in like a dead spot. And then there should be another spot where if you kept walking, all of a sudden it would sound very loud again. So that's kind of what happens with a phase shift. So kind of a weird effect, but that's what it sounds like.
And what happens if you use multiple sets of speakers?
It depends where you put them. So if you put like all the left speakers on that side of the room and all the right speakers on that side of the room, it would pretty much be the same effect, but you could get more of the effect. It would be almost like, it might change where the dead spots are a little bit because you have a lot more. Like if that whole wall was sound, it would change where the dead spots are a little bit, but there should still be a spot, like if you did it outside and you had a wall of speakers where you could stand and you wouldn't hear it as loud. Multiple speakers would kind of complicate it a little because then your sound isn't coming from a single point. If you think of it like this. Sound comes out as a wave. Here's a point, and the sound comes out like that. Like that. So when you have 2 points it's actually relatively easy to kind of figure out what the pattern of intersection looks like. But then when you throw like another sound source in there, now you're getting more sound waves. So it kind of really complicates what's happening in like this area right here. So more speakers, it would be a little more complicated to figure it out. That's why 2 single point sounds, that's the best for demonstrating this. Yeah.
Isn't that how they make like noise canceling stuff?
Yeah.
They kind of just can't.
Yep. So you can cancel out, like there are some high-end cars, if you read about it, that cancel out engine noise with sound. And you can't really do it everywhere, like if you're standing outside the car or inside the car, but it's not a big deal to do it everywhere. All you got to do it is in one spot where the driver sits, and maybe the passengers if you can. If you can cancel out the sound in that small area, even if it's louder somewhere else, that's fine. You can cancel it in that one spot. Sounds that look simple mathematically, like this one, very simple wave, very, very easy to cancel out that sound. But if you've got something like this, I'm going to show you a more complicated looking sound. And it's the sound that you're hearing right now. So when you look at a picture of my voice, it's not just like a single tone. It's a more complicated sound. There's all kinds of frequencies in my voice. The volume is changing all the time. That's why it's a little harder to tune me out sometimes. Maybe it isn't, I don't know. But that's why you could probably sleep with like they have sound machines, right? It makes the exact same sound, like sometimes like just like a white noise sound. That's a very constant, simple sound that after you hear it so long, it's like you're not even hearing it anymore. It's like it's just in the background. And then you only notice it when somebody shuts it off. It's like, whoa, it's really quiet. So they can cancel out engine noise because engine noise is very constant. Like engines don't, like if you're just idling, it pretty much sounds the same when it's just sitting there, you know? So. If you whistle, it would be like if I whistle, that would look kind of like, I can't keep it perfectly constant, but you could see it look like a sine wave. And then if you get different frequencies at the same time, the picture gets a little more complicated and all kinds of stuff.
I like
Yeah. So that's an oscilloscope, and we'll come back and we'll look at that more later on tomorrow. All right. So let's see if we can graph a couple phase shifts. So first thing I want to do is figure out what kind of transformation it is, because on the test I won't tell you. Well, I'm adding or subtracting, and it's in the parentheses. That means it's a phase shift. So in a phase shift, what values do not change at all? The y's. And we're doing sine. So if you go back to the sine table in your notes, what are the y values for sine? 0, 1, 0, negative 1, 0. Basically, the way a problem like this is graded, you get 1 point for each x and y value you get right. So you get 5 points for that part of the table. Now we got to do something with the x's. Okay, I need a little more. Let me get rid of this. A little more space. So, what are my original x values? And it doesn't matter, sine and cosine, they're the same. Yep.
0, pi over 2, pi, 3 pi over 2.
And now I'm going to do something to all those values. Am I going to add or subtract? Yep.
Add.
I'm going to add. And how much am I going to add to each one?
Pi over 2.
I'm going to add pi over 2. All right. First one, that's pretty straightforward. 0 plus pi over 2 is just pi over 2. Second one, pi over 2 plus pi over 2. They already have a common denominator. So it's something over 2. And what's pi over 2 plus another pi over 2? Okay, 2 pi over 2. Now, I'm going to come back and reduce that in a minute, but that's what it is for now. The third one, well, pi doesn't have a denominator. What could I make the denominator? I can put in a 1. And now to add these up, you need a common denominator. What's the common denominator between 1 and 2? 2. So I would have to double the bottom, but then I have to double the top. 2 pi over 2 plus 1 pi over 2. 3 pi over 2. The next one already has a common denominator. 3 pi over 2 plus 1 pi over 2. 4 pi over 2. And now you could do a common denominator for the last one, or just look at the pattern. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. Now, since I didn't reduce, it made the pattern easier to see. Now I'm going to go back and reduce it. Pi. And we'll make this one 2 pi. I usually reduce as I go, so from now on, that's how I'll do it. But I just wanted you to see the pattern. So 1 point for each x, 1 point for each y. That table would be 10 points. Any questions on that? Bless you.
Thank you.
And now the last thing is to make a sketch. Well, the y values are easy to label. We go up to 1, we go down to -1. So I would just go like this. This is going to be my x. That's going to be my y. Now, you can label an axis any way you want as long as you're consistent. Okay? You can't do something like this. If you were making a number line, you can't go 1, 2, 5, 6, 7. Right? You can't say I'm going to go by 1s, and then I'm going to switch to going by 3s, and then I'm going to go back to 1s. Right? You got to go by the same thing the whole time. So if we look at our labels, these are all equally spaced. If you look at it in degrees, that's 90, 180, 270, 360, 450. They're all plus 90, or plus pi over 2. That's why we saw the nice pattern. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. Nice pattern. I'm going to use these as my labels. Okay? They're all equally spaced, and it's a lot easier to graph if I use those as my labels. If I label these like 0, 1, 2, 3, 4, 5, 6 on the x-axis, that's going to be awful. Because then I got to find like 3.14, 6.28. That's going to be a mess. So just label them like this. Pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2. And now I'm just going to make it a little smaller so I can plot my points. Okay, so pi over 2, 0. Pi, I'm at 1. 3 pi over 2, 0. 2 pi, -1. It's hard to see from the side. And 5 pi over 2, I'm at 0. So there's the 5 points that are going to make my wave. And it'll look pretty much like that. Try to make it look curved. Okay? Nothing about a sine or cosine function is a sharp turn. Everything is curved. Okay, so in the homework, what you'll have to do is draw that. And then I have a separate one, but I'm just going to do it on the same one. Here's the original. Right there. So the original would have started at the origin. Just look back at your table. And the new one has been shifted to the right exactly pi over 2 radians. You don't have to draw, on this one, you don't have to draw the original. You can just draw the final answer. That's it. That's how you do a phase shift. Any questions on that one? Of the 2 transformations we're going to look at, this is the harder one, because you've got to do all the arithmetic with the pi column. When we do vertical shift, that's what we'll finish up with. That's easy, because all you're doing is arithmetic with zeros and ones, and negative ones. So that arithmetic is much easier. Okay, let's look at this one. Okay, first, I know it's a phase shift because I'm adding or subtracting in parentheses. So for phase shift, someone remind me again what values stay the same? Y's. What are my y's for cosine? We haven't done that one yet.
1, 0, negative 1, 0, 1.
There you go, half the table's done. Original x's are the same x's we just had before. Probably have these memorized by the end of tomorrow. 0, pi over 2, pi, 3 pi over 2, 2 pi. Now, what am I going to do to all 5 of those x values? Subtract, because we're always doing the opposite for phase shift. And what are we subtracting? Pi. Well, the first, the third, and the fifth, those are quick. 0 minus pi is how much? And pi minus pi? And 2 pi minus 1 pi? Pi. You don't have to do it like that, but I did them because they're fast. Now, let's do this one. Pi over 2 minus pi over 1. Common denominator is 2. Double the bottom, double the top. 1 pi over 2, take away 2 pi over 2. Negative pi over 2. And it's going to be exactly the same thing here in terms of your common denominator. Double the bottom, double the top. 3 pi over 2, take away 2 pi over 2.
Pi over 2.
Pi over 2, yep. And those are all nicely spaced because you took values that already were equally spaced and you subtracted the same thing from every one of them. So they're still equally spaced. All right, so let's make our graph. Label your y-axis, and you do have to label your x-axis. If you don't, I'm going to assume you're going by ones, and that's not what you want to go by. So you'd lose points for the graph on that. So let's start with negative pi. Negative pi over 2. You don't have to label 0, but 0 is the axis. Pi over 2 and pi. So if we look at it in degrees, I've made each section worth 90. That's negative 180, negative 90, 0, 90, 180. Okay, now let's do our sketch. So we've got negative pi 1, negative pi over 2, 0, back to negative 1, 0, and 1. Now, that looks kind of like a V shape, but remember, it's a wave, and you're sketching this part of it. It's kind of like a V shape, but it should have a little curve to it. So just do the best you can. Try to make it look curved. Just don't draw it like this. It's not what I do. Any question on that one? All right, we'll do one more phase shift, and then we'll finish up with the easier one, which is vertical shift. So on this one, I'm going to make the table for you quickly. I'm going to assume everybody could subtract pi over 4 and get the common denominator. But I want to go through the graph itself. So y's would stay the same. Just look those up in your table. Now, you would subtract pi over 4 from all the x's in your table. So this is what you would get. Negative pi over 4. Pi over 4. 3 pi over 4. 5 pi over 4. 7 pi over 4. I can do, like, I'll do this one just to show you how that happens. If if you take 2 pi and subtract pi over 4 from it, do you have a common denominator if you just leave it like that? No. What's the common denominator? 4. Multiply the bottom by 4. Multiply the top by 4. 2 times 4 is 8. 8 pi over 4. Take away 1 pi over 4. That's how I got 7 pi over 4. And you could do that for all of them. All right, so there's your table. Questions on that? Let me set up a number line. Okay, just watch this part for a second before you write it. I'm going to put 0 right in the middle, and then I'm just going to put some more marks on it. Okay, I'm going to put, and I'm going to do these in degrees just so you can see something. That's negative 45, 45, 135, 225, 315. I just know them because I'm working with degrees and radians a lot. So let's put negative 45 right there. Oops, negative 45. So this is 0. I'll make that a special color. So since I put negative 45 where I did, how much is it worth to get from one tick mark to the next? Like how much is each mark worth?
45 degrees.
Each mark is worth 45. Now, let me write these numbers down. Negative 45, 45, 135, 225, 315. Each mark is worth 45. What's the spacing between each x value? Like, what do you add to this one to get the next one? Yeah?
90.
You add 90. So let's look at where 45 would go. 45, you could put right there because it's 1, 2 tick marks away. Each tick mark is 45. Negative 45 and 45 are 2 tick marks away. Now, where would 135 go? Yep.
2 spaces to the right.
2 spaces to the right. You can't put it here. It wouldn't work because that's a gap of 45. 135 is 90 away from 45, so you have to go 2. So the point here is you end up skipping one. Okay? I think it's easier to see that you skip it when you do it in degrees. It's not easy for most people to see it when there's pi mixed into it. But I'm trying to show it in degrees. 225, 315. You skipped 0. Okay? You skipped that right off the bat. Put negative 45, you skipped 1, and then you put positive 45. If you skip 1, you're going to have to skip 1 every single time. All right? So now let's set up the same thing, but now I'm going to do it with my radians. I've got negative pi over 4. I'm skipping the 0. Okay? That one's being skipped. And then the next one, I'm putting it pi over 4. So now the mistake some people make is they put 3 pi over 4 right there. No, you can't. For the reason I just showed right up here. I'm going to skip putting a point at 0, so I'm going to skip every single time. I might need more space too, I'm not sure. So 3 pi over 4, 5 pi over 4, 7 pi over 4. And you'll know if you should have skipped something and you didn't, because your graph will look like this. It'll look like really squished in one part and stretched in the other, when it should always look nice and even. So you can tell when you draw it. Okay, so let's make our table. So 0. Pi over 4, I'm at 1. 3 pi over 4, I'm at 0. That looks nicely spaced so far. 5 pi over 4, negative 1. Back to 0. To me, all those dots look nicely spaced. If you had put 3 pi over 4 in the wrong spot, you would have had it here if you didn't skip. That looks off to me. the points don't look nicely spaced now. And I would have something that looks more squished in the beginning than it does at the end. Okay, so let me put it back where it should be. Now draw it. That looks good. That's the trickiest type of phase shift you could ever have. It never gets any trickier than that. But, any question on phase shift? The last one we'll look at, this one's a little easier, it's a lot easier, is the vertical shift. Vertical shift is when you shift it up and down. There's two things that make vertical shift easier. One, the arithmetic is with easy numbers. Ones, negative ones, and zeros. The second thing that makes it easier is you don't do the opposite. If you add, that will move it up, which makes sense to me. I think when I add something positive, positive is up. If I subtract, that brings it down. Negative, down. So you're still adding and subtracting. It's exactly the same thing as phase shift in terms of the operation. But it's where you're doing it. You're not inside the parentheses. You are outside parentheses. Okay? In order for that to be a phase shift, you would have to group the x and the 2 together. Now that's a phase shift. When you add and the letter and the number are not grouped together, vertical shift. So when you shift up and down, if you had a coordinate, which values are going to change? The y's. Okay, so this time, your y values are going to change, which means what is going to stay the same? X. And that's great when the x's stay the same, because now all the fractions with pi, we don't need to touch them. Every problem we do for a vertical shift today, your x's are going to be 0, pi over 2, pi, 3 pi over 2, 2 pi. That will not change on any problem. So we don't have to touch the stuff with pi. So it's the y's that are going to change, but the arithmetic is super easy. All you do is take the original y values and add or subtract d. Again, what's d? D is just the number that was at the end. How do you know if you should add or subtract it? Look at the number. If it's a positive number, add it. Negative number, subtract it. Don't do the opposite. For some reason, I think people get it in their head, oh, I can always do the opposite. No, this one you don't. So on your reference sheet, maybe make a note about that or put an example or something. Don't do the opposite. Let's look at an example. How do you know that that's a vertical shift and not a phase shift? Because they both use addition. So how can you tell the difference? Yep. It's not in parentheses with the x, the letter. Okay? It's not in parentheses with the letter. So, Michael just told us, or he confirmed why it's a vertical shift. X's stay the same. Greta, can you remind me, I know I've said them a few times, but can you remind me what my x's are?
0, pi over 2, pi, 3 pi over 2, and pi.
2 pi. All right. And the y's for cosine, we just did that a couple problems ago. 1, 0, negative 1, 0, 1. And now, Alec, what am I going to do to all of these y values?
Just add 2 to them.
Just add 2. So I'm going to get 3, 2, 1, 2, 3. Done. That's it. That's the whole table. Just add 2. as long as I did it correctly. Yep. Any questions on that one? All right, and now I'll set up my axis, make my labels, and then that'll be it. So we've got 0, 1, 2. I would just go by ones on the y-axis because you've got plenty of room. And then on the x-axis, I've got 0, pi over 2, pi, 3 pi over 2, 2 pi. It's kind of better if you put your labels lower, because if you don't, you end up drawing right over them when you graph. So I try to put my labels in a spot where they're out of the way. If you end up drawing over your labels, it's not a huge deal as long as I can still read them. All right, so 0, 3, pi over 2, 0, pi 1, 3 pi over 2, and 2 pi back to 3. So whenever we sketch a cosine, that's the part of the wave that looks like a V, but just try to make it look a little curved. Okay? So that's good enough. So that's a cosine function shifted up 3 units. As far as an effect on the sound, I don't really know one. 3 out of 4 of the transformations we study, I can connect it with sound and kind of do a little demonstration for you. This one I can't. This is the only one I'm not sure of the effect on the sound. Any questions on that? Right. So if I were to do that one, is that a vertical shift or a phase shift?
Vertical.
Vertical. Which way is it going to move it? Down 3. So what do you do to a coordinate to move it down 3?
Subtract it.
From the y's. Yep. That's how you do that one. Okay, so these 7 problems, I have them on a worksheet. So if you lose the worksheet, you can get them from the video, but you don't need to write them all down because they're on a worksheet. Or you can write them down too. Either way. So we looked at all the shifts today. Took a little more time than I thought playing around with the phase shift, but tomorrow we'll look at the stretches.